Hello and welcome to this Electrical Principles training video. In this video we're going to revisit our Lego DC motor and we're going to have a look at why this works in the way that it does. So we're going to tie in some principles of electrical science that we've looked at in a previous video of what happens when we pass electricity through a conductor, and then we're also going to tie in Fleming's left-hand rule for motors in order to understand why the motor turns in the direction that it does. We'll also see how it's possible to reverse the direction of this motor. So what we're going to do is we're going to bring the camera in and we'll have a look in a little bit more detail about why this motor works in the way that it does. Okay, so let's just prove that our Lego motor is still operating and that we haven't messed this up at all since the last video. Just check that this is going to work. And that's always encouraging to see that that still operates. So now we can see that the Lego motor is still working. Let's have a little think about how it's working. So we saw in a previous video how Fleming's left-hand rule works for motors. We saw that if you put a conductor inside a magnetic field and pass current through it, then Fleming's left-hand rule will tell you which direction that conductor will move in. And that actually defines the direction of rotation of our DC motor. So we were injecting current in this direction in the motor. So we had the positive connection on this side. So the current was flowing away from us down that side of the motor. And then it came around the back and flowed towards us and out of the circuit in this direction. So how do we figure out which way the motor is going to turn? Well, again, using Fleming's left-hand rule for motors, if you remember, the second finger on your left hand represents the direction of the current flow. So on this side of the motor, the current was going away from us like that. And then your first finger is the direction of the magnetic field. So this is the North Pole and this is the South Pole. I know that from experimentation. So this is the North and this is the South. So that means that I put my knuckle at the North and I point towards the South, and then notice where my thumb is. So remember, we're looking at this side of the motor. So I've got current going away, magnetic field going in that direction, which means that my thumb is pointing downwards, and that was the direction that the motor went in. On that side it went down. Now just for the sake of completeness, let's think about what's happening the other way. In this side of the motor, the current was coming towards us, so my second finger is now pointing towards us. The direction of the magnetic field hasn't changed, we've still got the North and the South, so my knuckle of my first finger is at the North Pole, so knuckle North pointing towards the South Pole with my first finger for flux. And on this side of the motor we can see that the thumb, which it gives us the direction of motion, is pointing upwards, and that indicates that the motor will go down on this side, up on this side, and rotate in that direction as we saw was happening. Hopefully at this point it's fairly clear to see how we could reverse the direction of motor. We could simply reverse the input onto the machine, so we could swap the positive and the negative round and have that spinning the other way. Or we could reverse the magnetic poles around, so we could swap these over and the motor would then turn in the opposite direction again. So let's just prove that we can change the direction of rotation by connecting across here like this. I've changed the polarity of the supply, if you like, so now I've got the positive side on this side and the negative side on this side. So let's just see if the motor changes its direction. And indeed you can see there just from that initial burst that indeed it is going to change its direction. There we go. So now it's rotating the other way around. So we've seen that the motor does turn, we've seen how we can reverse the motor. However, it's very important at this point that we now think about, why does that happen? What is the reason for that conductor moving? We've seen it in experimentation in a previous video with our electronics kit. We've seen it in action in this video, in a previous video with our Lego motor. But why does it happen? Why does the conductor move in that direction? Well, let's explore that idea next. Now you can see on the screen that we've got here a simplified version of our Loctronics experiment. So you can see that we've got a North Pole and we've got a South Pole. You can see there that between that North and South Pole there will be lines of magnetic flux, and they will go in this direction, and they will go from north to south there. Underneath our magnetic field at the minute, so we're just considering this as a separate entity at the moment, we can see a cross-section of a conductor. And that cross-section has a cross in the center of it, which indicates that current is going away from us. Now, if we were to put that conductor inside the magnetic field, we could use Fleming's left-hand rule to figure out which way the conductor will move. But why does it move? And why does it move in the direction that it does move? Well, let's think about this. Our conductor, when we pass current through it, if the current's going away from us, we'll see that that will generate a magnetic field around the conductor, and that magnetic field will have a clockwise direction when the current goes away from us. It will look like this. Now, what happens if I put the current-carrying conductor into the magnetic field, very much like we've got inside our Lego motor here? Well, if I put that inside there, you can see that we've got two magnetic fields, one being generated by the conductor, one being generated by the magnets. Now, my question to you now is, what is wrong with this drawing? Well, hopefully, if you've seen another video in this series, you'll know that we're breaking one of the rules of magnetic flux here, and that is that lines of magnetic flux cannot cross over each other. So this drawing is inaccurate. It shouldn't look like this. What actually happens is that while we can't cross lines of magnetic flux, and while we can't break lines of magnetic flux, what we can do is we can distort lines of magnetic flux. And actually, the magnetic fields would start to look like this. So you can see that the magnetic field from the bar magnet is being distorted by the magnetic field from the conductor. And lines of magnetic flux do not like being distorted. They like to be their natural shape, which in this case would just be pretty much a straight line between the North and the South Pole. So how's this going to get resolved? Well, let's think about some of the other laws of magnetic flux that we know. Look at the top side of the conductor. What do you notice there? Well, at the top side, you can see that the lines of magnetic flux are all going in the same direction. So the lines of magnetic flux created by the bar magnet are going from the North to the South Pole. So in this case, they're going from left to right. And then you can see also that the lines of magnetic flux that surround the conductor at the top of the conductor also go in the same direction. They also go from left to right at that point. So that means that those lines of magnetic flux, we know from a previous video that lines of magnetic flux that have the same direction will be repelled from each other. And therefore, because there's two things at play here. Number one, the lines of magnetic flux want to go back to their natural shape. And also we've got this repelling action created by lines of magnetic flux that have the same direction. If that conductor is free to move, then we can see that the conductor will be pushed out of the magnetic field downwards, which actually corresponds with Fleming's left-hand rule also. So now let's take this back to our Lego motor and just confirm what we've talked about here, the application of it. So again, just bear in mind that in this Lego motor, the current is going away from us in this side when we did our experiment earlier, which means we've got current flowing away from us. We've got a North Pole and a South Pole. So between these two magnetic poles, there are invisible lines of magnetic flux. When we introduce current into the circuit, the current flows away from us down this side of the conductor, and we get a magnetic field generated around this conductor. Now, because we've wrapped this into a coil as well, that means that the magnetic field becomes stronger around the conductor here. And that means that it will turn with a bit more force, basically. So the magnetic field generated by the current flowing through the conductor sits inside the magnetic field being generated by the two fixed magnets here, and that creates this kind of distorted magnetic field. So the lines of magnetic flux would come across here and kind of be distorted, and they just want to snap straight, and also we get that repelling action that we spoke about when we were looking at the images on the screen previously, and therefore this motor turned in that direction like that. Now, it's interesting with the DC motor because we've got this little fella on the end here, the commutator, and what that does is it keeps the positive connection flowing down this side of the motor at all times. An AC motor works a little bit differently to this, but in a DC motor, the current is always flowing in the same direction inside the armature, the rotating part of the motor here. So as this rotates around, so if we've got a connection on here, as this rotates around, so the current goes away from us, and then as it turns, The connection at this point is broken between the two connections that we had from the outside world. And at this point, the momentum of the motor just carries it over until it gets to here. And then at that point, once we make contact again with our two probes that we were holding on there, can you see that the positive connection is still on this right-hand side, therefore the current is still going away from us, which means that will then again be pushed down in that direction. And that's how that continuous rotating motion is generated. So in this video, we've seen how Fleming's left-hand rule applies to the action of a DC motor, and we've also gained a deeper understanding of how Fleming's left-hand rule actually works, why the conductor moves in the direction that it moves in. We've also seen how to reverse the direction of the motor and the reason why the motor continues to rotate around. So at this point, all that's left to say is thank you very much for watching.